There's a whisper from the very edge of time, a signal so faint it's almost lost in the silence of space, yet it carries the story of everything. Picture this, a glow so ancient it predates the first stars, the first galaxies, even the atoms that make up your body. This is the cosmic microwave background, the oldest light in the universe, and it's been traveling toward us for nearly 14 billion years. It's not just a relic of the past, it's a living message, a cosmic fingerprint left over from the moment the universe burst into existence. And what it's telling us could rewrite everything we thought we knew about reality. Think about the last time you stood under a clear night sky, staring up at the stars. What you're seeing is history, light that's taken years, centuries, even millennia to reach your eyes. But the cosmic microwave background, this is light from a time before time as we know it, a snapshot of the universe when it was just a newborn, barely 380,000 years old. It's the afterglow of the Big Bang itself, stretched and faded over eons into a faint microwave hum. Yet within that hum lies the blueprint of the cosmos, the seeds of galaxies, the pull of dark matter, even the ghostly influence of dark energy, the force that's tearing the universe apart. Why does this matter to you? Because this isn't just a story about distant stars or abstract physics. It's a story about us, every atom in your body, every planet, every speck of dust in the vastness of space. It all traces back to that primordial light. The cosmic microwave background is our ultimate origin story, a window into the moment everything began, and scientists are still decoding its secrets, uncovering clues about how the universe grew, how it's changing, and where it might be headed billions of years from now. So let's dive into this celestial time capsule, peel back the layers of the oldest light in existence, and discover what it's still trying to tell us about the cosmos and our place within it. It all started with a frustrating mystery, a persistent hiss that refused to go away. In 1964, two astronomers, Arno Penzias and Robert Wilson, were working with a massive, ultra-sensitive radio antenna in New Jersey, originally built for satellite communication. But no matter where they pointed the antenna, this strange, unshakable static followed them, like an uninvited guest at the edge of every observation. They checked every possible cause, cleaning out pigeon nests, recalibrating equipment, even shielding against interference from nearby New York City. Nothing worked. The noise was everywhere, evenly spread across the sky, and it defied all explanation. What they didn't realize at first was that they'd stumbled upon the echo of creation itself. That annoying static, it was the cosmic microwave background, the faint afterglow of the Big Bang, still lingering in the void after nearly 14 billion years. At the same time, just 30 miles away, a team of physicists at Princeton University had been searching for this exact signal, a relic radiation predicted by the Big Bang theory. When Penzias and Wilson heard about their work, the pieces fell into place. That unexplained noise wasn't a flaw in their equipment. It was the oldest song in the universe, humming softly in every direction. The discovery sent shockwaves through science. For decades, the Big Bang theory had been just one of several competing ideas about how the universe began. Some scientists even argued for a steady-state model where the cosmos had no true starting point. But the cosmic microwave background changed everything. Here was hard evidence that the universe had indeed been born in a fiery explosion, expanding and cooling ever since. Penzias and Wilson's accidental breakthrough earned them the Nobel Prize in 1978, but its true value went far beyond awards. It gave us a time machine, a way to peer back to the universe's infancy and test our boldest ideas about reality. And the wildest part, that faint microwave glow isn't just a relic, it's a treasure map. tiny variations in its temperature, imprinted when the universe was smaller than a single atom, reveal the seeds of everything we see today. Those microscopic ripples grew into galaxies, clusters, and the vast cosmic web we now observe. Without that static, without Penzier's and Wilson's stubborn curiosity, we might still be guessing about how it all began. Instead, their discovery locked in place one of humanity's greatest triumphs. We cracked the code of the universe's birth certificate, and we're still deciphering what else it has to say. To understand the cosmic microwave background, you have to travel back to a time when the universe wasn't just young. It was unrecognizable. Picture a cosmos so dense and hot that light couldn't travel freely. Space was a swirling soup of charged particles, protons and electrons constantly colliding, trapping photons in a chaotic dance. But then, around 380,000 years after the Big Bang, something extraordinary happened. The universe had expanded enough to cool below 3,000 degrees, allowing electrons and protons to finally combine into neutral hydrogen atoms. In that moment, the fog cleared. Light, once trapped, was suddenly set free, streaming outward in every direction. That first burst of liberated light is what we now detect as the cosmic microwave background, a fossilized echo of the universe's first dawn. What's incredible is how perfectly this relic has been preserved. Over billions of years, the expansion of space stretched those primordial photons from visible light into microwaves, cooling them down to just 2.7 degrees above absolute zero. Yet despite traveling for nearly 14 billion years, the CMB reaches us with remarkable uniformity, bathing the entire cosmos in a near-identical glow. It's like standing in a vast, silent room where every surface hums with the same faint tone, a tone that holds the secrets of how everything began. But look closer, and the CMB isn't perfectly smooth. Tiny fluctuations, variations in temperature as slight as 1 part in 100,000 paint a hidden blueprint across the sky. These imperfections are cosmic gold. They represent the faint gravitational fingerprints of matter clumping together in the early universe, the seeds that would eventually grow into galaxies and galaxy clusters. Without those microscopic ripples, gravity would have had nothing to work with, and the universe as we know it, with its glittering cities of stars, might never have formed. The CMB isn't just a static image, it's a dynamic record. By studying its polarization, the subtle twisting of light waves as they interacted with matter in the early universe, scientists can trace the influence of gravitational waves from the Big Bang itself. It's like finding ripples in a pond and realizing they were made by a pebble tossed moments after the universe began. This light doesn't just tell us where we came from, it hints at forces we're still struggling to understand, like dark energy's relentless push or dark matter's invisible grip. And here's the most humbling part. When you look at a map of the CMB, you're not just seeing the past, you're seeing the limits of observable reality. That glow marks the edge of our cosmic horizon, the farthest light could have traveled since the beginning. Beyond it lies the unknown regions of space so distant their light hasn't had time to reach us yet. The CMB is both a beginning and a boundary, a reminder that even as we uncover the universe's secrets, there will always be more mysteries waiting in the dark. That faint microwave glow blanketing the cosmos isn't just a relic, it's a cosmic detective's dream. Hidden within its near-perfect uniformity are whispers of the universe's first moments, imprinted like fingerprints in light. Those tiny temperature variations, no bigger than 1 part in 100,000, might seem insignificant, but they're the universe's way of leaving breadcrumbs. Each slight fluctuation is a snapshot of density, a place where matter was ever so slightly more crowded or sparse in the infant cosmos. And from those microscopic imbalances, gravity wove the tapestry of everything we know. Imagine tossing a handful of pebbles into a still pond. The ripples spread outward, interacting, merging, growing. The cosmic microwave background works the same way. Those initial quantum fluctuations, random, subatomic twists in the fabric of space-time, were stretched to cosmic scales during a brief but explosive period called inflation. In less than a trillionth of a second, the universe expanded faster than light itself, magnifying those quantum whispers into the gravitational seeds of future galaxies. Without this rapid growth spurt, those fluctuations might have remained too small to ever matter, but inflation turned them into the foundation of our universe's large-scale structure. Here's where it gets even more fascinating. By mapping these temperature variations with satellites like the Planck Observatory, scientists can reconstruct the universe's baby album. Warmer spots in the CMB mark regions where matter was slightly denser, destined to become galaxy clusters. Cooler patches, those are the cosmic valleys, the voids between the threads of the cosmic web. It's as if we're holding an ancient, weathered map where X doesn't just mark the spot. It marks every spot where stars would one day ignite, but the story doesn't end there. The patterns in the CMB also reveal the universe's ingredients. The way those fluctuations are distributed tells us precisely how much ordinary matter, and dark energy make up the cosmos. It's like decoding a recipe from the way flour and sugar are mixed in a baked good, and the results are startling. Less than 5% of the universe is the stuff we're made of: atoms, planets, stars. The rest is dark matter's invisible scaffolding and dark energy's mysterious push. Perhaps most mind-bending of all, the CMB lets us test theories about the universe's very birth. The pattern of fluctuations aligns eerily well with predictions from inflation, but it also leaves puzzles. Why, for instance, is the universe so uniform on large scales? How did regions now billions of light-years apart once share the same temperature? These are clues that our cosmic origins might be even stranger than we've imagined. The CMB isn't just a time capsule, it's a mirror reflecting back not just how the universe began, but the limits of our understanding. And with every new observation, we're peeling back another layer of this cosmic onion, revealing questions we didn't even know to ask. Before Penzias and Wilson stumbled upon that persistent hiss, cosmology was a battleground of competing ideas about how the universe began. Some scientists championed the steady-state theory, the idea that the cosmos had always existed, with new matter continuously created to fill the gaps as space expanded. Others proposed cyclical models where the universe collapsed and reborn in endless cycles. The Big Bang theory, radical as it sounded, was just one possibility among many. But everything changed when that faint microwave whisper entered the scene, carrying with it two extraordinary features that would silence nearly all debate. First, the cosmic microwave background revealed a near-perfect blackbody spectrum, a precise thermal fingerprint matching exactly what physicists predicted would remain from a hot, dense origin. It's like finding a fossil with every bone perfectly aligned to a prehistoric creature's theoretical skeleton. No other known process in nature could produce such a flawless thermal signature except the cooling embers of an initial cosmic fireball. Second, the CMB's staggering uniformity, its temperature varying by less than 0.1% across the entire sky, pointed to a shared origin, a moment when the entire observable universe was smaller than a peach, hot enough to blend everything into perfect equilibrium. These weren't just clues, they were smoking guns. The steady-state theory couldn't explain why space was filled with ancient radiation, bearing all the marks of an explosive beginning. Alternative models strained to account for the CMB's exquisite blackbody curve without invoking a hot, dense past, but the Big Bang theory, it predicted both. The match was so precise that even skeptics had to concede. This was evidence beyond reasonable doubt. The universe had a birthday, and the CMB was its faded candle glow. Yet the real triumph wasn't just confirming the Big Bang. It was realizing how much this ancient light could still teach us. The CMB's uniformity became a puzzle in itself. How could regions now billions of light years apart have reached the same temperature without ever being in contact? This horizon problem led physicists to propose cosmic inflation, a mind-bending idea that the universe underwent a fleeting, exponential expansion in its first sliver of a second. Inflation would stretch quantum fluctuations into cosmic scales, explaining both the CMB's large-scale smoothness and its tiny, crucial irregularities. What's remarkable is how this evidence keeps giving. Modern satellites like WMAP and Planck have measured the CMB's temperature variations with such precision that we can now calculate the universe's age 13.8 billion years, its shape flat to within a fraction of a percent, and even its ultimate fate, continued accelerated expansion. The CMB didn't just settle an old debate, it opened a new era of precision cosmology, where we're not just telling stories about the universe's birth but testing them with forensic detail. And every new observation reminds us the echoes of creation are still speaking if we're patient enough to listen. Those faint ripples in the cosmic microwave background, those barely their temperature variations, might seem like cosmic static at first glance. But zoom in and you'll find they're anything but random. These anisotropies, as scientists call them, are the universe's way of whispering its deepest secrets. Each slight fluctuation, some as small as 1 part in 100,000, is a frozen moment from a time when the cosmos was a seething, turbulent infant. These aren't just imperfections, they're the genetic code of everything we see today, encoding the distribution of matter, the tug of dark energy, and even the echoes of the universe's first trillionth of a second. Take a closer look at a CMB map, and you'll notice a pattern: hotter spots where matter was denser, cooler patches where it was thinner. These variations didn't emerge by chance. They were sculpted by gravity's invisible hand, with dark matter playing a starring role. In the early universe, dark matter's gravitational pull acted like a cosmic scaffold, guiding ordinary matter, the stuff that would become stars and galaxies, into clumps and filaments. The CMB's ripples are essentially snapshots of that process in its earliest stages, showing us where matter began to gather before the first stars flickered to life. But here's where it gets even more intriguing. The size of these fluctuations isn't arbitrary. They follow a precise mathematical pattern, one that aligns eerily well with predictions from cosmic inflation, the theory that the universe underwent a brief, explosive expansion in its first instant. Inflation would have stretched quantum fluctuations, those tiny, random twists in space-time, into cosmic-scale density variations. The CMB's anisotropies are essentially those quantum ripples, blown up to universal proportions. It's as if we're looking at a magnified imprint of the universe's quantum origins, frozen in light. Then there's the mystery of the CMB's largest-scale patterns. Why does the universe look so similar in all directions, even in regions that could never have been in contact? This horizon problem is one of the biggest clues that our cosmic history might be even stranger than we've imagined. Inflation offers a solution. If the universe expanded faster than light in its first moments, distant regions could have once been close enough to share temperature before being flung apart. The CMB's near uniformity, punctuated by those tiny ripples, is one of the strongest pieces of evidence we have for this mind-bending idea, and the implications don't stop there. By studying how these anisotropies are distributed, scientists can weigh the universe's ingredients with astonishing precision. The way matter clumps together in the CMB reveals the invisible grip of dark matter, while the overall geometry of those fluctuations hints at dark energy's relentless push. It's like taking a single fingerprint and deducing not just the suspect's identity, but their entire life story. What's truly humbling is that these ripples, these faint, ancient whispers, are still shaping the cosmos today. The denser regions mapped in the CMB grew into galaxy clusters, while the emptier patches became the vast voids between them. We're essentially seeing the blueprint of the universe's large-scale structure, a web of matter woven by gravity over billions of years. And as we refine our measurements, probing ever deeper into the CMB's subtle patterns, we're uncovering new puzzles like slight anomalies in certain directions that might hint at physics beyond our current understanding. So the next time you hear about the cosmic microwave background, remember, it's not just a relic, it's a dynamic, living record, a cosmic detective story written in temperature variations. And with every new observation, we're turning another page, uncovering clues about the forces that shaped our universe and the mysteries still waiting to be solved. Dark matter may be invisible, but its fingerprints are all over the cosmic microwave background. Think of it like this: when you see tree branches swaying in the wind, even if you can't see the air itself, you know it's there by the way it moves everything around it. The CMB works the same way. As this ancient light travels across the universe, dark matter's gravitational pull subtly bends its path, warping the light like a cosmic funhouse mirror. These distortions, called gravitational lensing, create faint but measurable patterns in the CMB's temperature map patterns that let scientists reconstruct the hidden skeleton of the cosmos. What's astonishing is the scale of this shadow play. Dark matter doesn't just nudge individual photons, it sculpts entire swaths of the CMB. Where dark matter clumps together, its gravity acts like a lens, magnifying some regions of the background while stretching others. By analyzing these distortions, researchers can create three-dimensional maps of dark matter's distribution, tracing its tendrils across billions of light years. It's as if we've been given night vision goggles to see the invisible framework upon which galaxies are hung. The revelations don't stop there. The CMB reveals not just where dark matter is, but how it behaves. The way these lensing patterns evolve over cosmic time confirms that dark matter moves slowly, what scientists call cold. Fast-moving particles would have smoothed out the universe's structure, but the CMB shows us a cosmos rich with clumps and voids, exactly what cold dark matter predicts. This alignment between theory and observation is one of the strongest validations we have for dark matter's existence, even if we still don't know what it's made of. Perhaps most mind-bending is how the CMB lets us weigh dark matter without ever seeing it. By measuring how severely dark matter bends CMB light, scientists can calculate its total mass. The results are staggering. Dark matter outweighs ordinary matter by a factor of 5 to 1. Every galaxy, every star, every atom in your body is just the visible frosting on an enormous, unseen cake. And thanks to the CMB, we're finally learning the recipe. But the story gets even richer when we combine CMB data with other cosmic clues. When scientists overlay dark matter maps from the CMB with observations of galaxy distributions, the match is uncanny. The places where dark matter pools, according to the CMB's lensing patterns, are precisely where galaxies cluster most densely. It's a cosmic handshake between two completely independent ways of mapping the universe, and it leaves little room for doubt. Dark matter is real, it's everywhere, and it's been shaping the cosmos since the beginning. What's next? As telescopes grow more sensitive, we're detecting finer details in the CMB's lensing patterns, hunting for hints about dark matter's true nature. Does it interact with itself? Does it decay over time? The CMB may hold answers to these questions too, written in the warped light of the universe's oldest messenger. Every new distortion we uncover is another piece of the puzzle, another step toward understanding the invisible force that built our cosmic home. There's a quiet revolution hidden in the cosmic microwave background, a revelation so profound it rewrote the future of the universe. For decades, scientists assumed the cosmos was expanding at a steady pace, slowing down under gravity's pull like a ball rolling uphill. But the CMB, combined with observations of distant supernova, delivered a shock. The universe isn't just expanding, it's accelerating, as if some invisible hand pressed down on the cosmic gas pedal. The culprit, dark energy, a mysterious force making up nearly 70% of the universe's total energy, and the CMB holds the key to understanding it. How can light from the universe's infancy tell us about its fate? It all comes down to geometry. The cosmic microwave background's patterns act like a cosmic ruler, measuring the universe's shape and size across time. When scientists compared the CMB's snapshot of the early universe with the distribution of galaxies today, they found something startling. The universe's expansion rate didn't match predictions based on gravity alone. Instead of slowing, space was stretching faster, as if dark energy were relentlessly pushing galaxies apart. The CMB's subtle temperature variations, particularly on large scales, revealed the exact moment when dark energy's influence began to dominate, around 5 billion years ago, overcoming gravity's grip and setting the cosmos on its accelerating path. But dark energy's signature isn't just in the expansion rate. The CMB's polarization, the faint swirls in its light caused by ancient gravitational waves, offers another clue. These patterns suggest dark energy behaves like a cosmological constant, a term Einstein once called his greatest blunder before discarding it. Now it's back at the center of physics, representing the energy of empty space itself. Yet the CMB also hints at puzzles. If dark energy's strength changes over time or interacts with matter in ways we haven't imagined, its fingerprints should be detectable in the background's detailed structure. What does this mean for the universe's ultimate fate? If dark energy remains constant, the acceleration will continue indefinitely, leading to a big freeze, galaxies drifting so far apart that their light can never reach us, leaving future skies eerily dark. But if dark energy grows stronger, it could tear apart galaxy clusters, stars, even atoms in a catastrophic big rip. The CMB's role in this cosmic drama is unparalleled. By refining measurements of its large-scale fluctuations, scientists are testing whether dark energy is truly constant or something far stranger. Here's the remarkable part. The same light that illuminates our origins is also guiding us toward the universe's final act. The CMB isn't just a relic, it's a prophecy written in microwaves, and as we decode its secrets, we're not just uncovering the past, we're glimpsing the destiny of everything. The shape of the universe isn't just a philosophical question, it's written in the cosmic microwave background, etched into those ancient photons like a celestial blueprint. For centuries we wondered, is space curved like a sphere, warped like a saddle, or perfectly flat? The answer changes everything from how galaxies move to the universe's ultimate fate. And thanks to the CMB, we've found a way to measure the cosmos itself. Think of it like this. Imagine drawing a giant triangle across the sky, with each side stretching billions of light years. In a flat universe, the angles of that triangle would add up to exactly 180 degrees, just like the geometry you learned in school. But if space were curved positively like a sphere or negatively like a saddle, those angles would shift. On a spherical cosmos, they'd bulge past 180 degrees. On a saddle-shaped one, they'd pinch inward. The CMB lets us test this on the grandest scale possible. By studying the apparent size of temperature fluctuations in that primordial light, scientists can effectively measure the universe's triangles and see how their angles behave. The results are staggering. After decades of analysis, from the COBE satellite to the Planck mission, the data points overwhelmingly to a flat universe, or at least one so close to flat that any curvature is too slight to detect. Those tiny temperature variations in the CMB appear at just the right angular scale, matching predictions for a cosmos where parallel lines never meet and the rules of Euclidean geometry hold true. It's as if the universe handed us a perfectly straight ruler, confirming that space isn't secretly bending on the largest scales. But here's where it gets even more profound. A flat universe isn't just a geometric curiosity, it's a clue to the cosmos's hidden ingredients. For space-time to be flat, the total density of matter and energy must be exquisitely balanced at what's called the critical density. Too much and the universe would curve inward like a ball. Too little and it would sag like a saddle. The fact that we measure flatness means the universe's energy budget, ordinary matter, dark matter, and dark energy combined hits that Goldilocks precision. And the CMB doesn't just tell us the universe is flat. It lets us weigh every component in that equation, revealing dark energy's dominance and dark matter's invisible grip. There's a beautiful irony here. The CMB, a remnant of the universe's fiery infancy, also encodes its far future. A flat cosmos with dark energy means expansion will continue indefinitely, galaxies fading into isolation as space stretches toward cold, empty stillness. But the story isn't entirely closed. Some theories suggest the universe might be so vast that any curvature is simply too subtle for us to measure, like an ant on a basketball mistaking its surface for a flat plane. Future CMB experiments probing even finer details may yet reveal whispers of curvature at scales beyond our current vision. For now, though, the CMB's message is clear. We live in a universe balanced on a razor's edge, its geometry so finely tuned that it reshapes not just how we see space, but how we understand the forces silently steering it. Every flicker in that ancient light is a data point in the greatest survey ever conducted, a map not just of where we've been, but of the shape of reality itself. To grasp how the cosmic microwave background tests inflation theory, picture blowing up a balloon with tiny dots drawn on its surface. As the balloon expands, those dots spread apart in perfect synchrony. No matter how far apart they drift, they share the same origin story. That's essentially what cosmic inflation suggests happened to the universe in its first trillionth of a second. Space itself stretched faster than light, smoothing out irregularities and magnifying quantum fluctuations into cosmic scale ripples. And the CMB, it's the ultimate snapshot of that process, frozen in time. The most striking evidence lies in the CMB's near-perfect uniformity. How could regions now billions of light years apart, regions that could never have exchanged heat or information, reach the same temperature? Inflation solves this horizon problem by proposing these areas were once neighbors, crammed together before inflation flung them apart. The CMB's uniformity isn't just a curiosity. It's a smoking gun, proof that the universe underwent a phase of ultra-rapid expansion long before the first stars flickered to life. But inflation's fingerprints go deeper. The pattern of temperature fluctuations in the CMB matches predictions with uncanny precision. Inflation would have stretched quantum fluctuations, random wrinkles in spacetime, into slight density variations across the cosmos. These weren't arbitrary, they followed a specific mathematical signature known as a scale invariant spectrum, where fluctuations appear equally at all sizes, like fractal patterns in nature. When satellites like Planck mapped the CMB's fluctuations, they found exactly this pattern, as if the universe had left behind a mathematical confession. Then there's the hunt for primordial gravitational waves, ripples in spacetime itself, generated during inflation's violent expansion. These waves would have left a distinct swirling pattern, or B-mode polarization, in the CMB's light. While definitive detection remains elusive, tentative hints in data from experiments like BICEP-2 have fueled intense research. Finding these waves would be like uncovering the universe's first seismic activity, direct evidence of inflation's explosive energy. Yet the CMB also poses challenges for inflation. Some models predict larger temperature variations at large scales than what we observe, while others struggle to explain subtle asymmetries in the CMB's distribution. These anomalies don't disprove inflation, they refine it, pushing physicists to explore more nuanced versions of the theory, from multi-field inflation to scenarios where inflation wasn't a single, smooth event but a series of fits and starts. What's remarkable is how the CMB transforms abstract theory into testable science. Inflation could have remained an elegant but untested idea. Instead, thanks to those ancient photons, we're conducting forensic analysis on the universe's first moments, probing physics at energies far beyond anything we can recreate in labs. Every new CMB map is like turning the pages of a cosmic history book, one written not in ink but in the faint afterglow of creation itself. Hidden within the cosmic microwave background's faint glow may lie the most explosive secret of all, ripples from the universe's very first tremors. These aren't just any waves, they're primordial gravitational waves, space-time vibrations generated during cosmic inflation's unimaginable expansion. Picture the universe's fabric stretching faster than light itself, quantum jitters magnified into cosmic-scale undulations that could still be imprinted on the CMB's polarized light like ghostly fingerprints. Detecting these waves would be like finding the first cry of a newborn cosmos. As inflation wrenched space apart, it should have created gravitational waves with unique swirling patterns in the CMB's polarization, what scientists call B-modes. Unlike the temperature fluctuations that reveal density variations, these twisting signatures would directly probe inflation's energy scale, telling us just how violent the universe's growth spurt really was. It's the difference between studying an explosion by its aftermath versus feeling its shockwave pass through you. The search for these signals has become one of cosmology's greatest detective stories. Teams have braved the thin air of Antarctica's high plateau and launched delicate instruments atop stratospheric balloons, all to catch these whispers from the dawn of time. In 2014, the BICEP-2 experiment made headlines with a tantalizing detection that turned out to be cosmic dust's misleading mimicry, a reminder of how fiendishly difficult this hunt truly is. Yet even null results teach us something profound. They constrain inflation's possible energies, ruling out some of its more extreme versions while guiding theorists toward refined models. What makes this pursuit so revolutionary? Primordial gravitational waves would carry information from energies 1 trillion times beyond what particle colliders can reach, offering a window into physics we can't recreate. Their detection could reveal whether inflation was driven by a single quantum field or a chorus of interacting forces, perhaps even hinting at connections to string theory's extra dimensions. The amplitude of these waves would tell us inflation's energy scale. Was it a gentle cosmic stretch or a cataclysmic event approaching Planck energy? But the implications go even deeper. If B-modes are found, they'd confirm that gravity, like light, has quantum properties, a staggering insight into how space-time itself behaves at microscopic scales. We'd effectively be witnessing quantum gravity's signature written across the sky, bridging Einstein's theory with the quantum realm. Conversely, If future experiments like the Simons Observatory or next-generation satellites fail to detect them, we might need to reconsider whether inflation happened at all, or if the universe's beginning holds surprises beyond our current theories. This isn't just about validating a 40-year-old idea. It's about whether we can peer beyond the veil of the Planck epoch, that mysterious era where time and space as we know them may have ceased to exist. The CMB's polarized light could be our only lens into that unfathomable moment, carrying traces of phenomena so exotic they redefine what we mean by the beginning. Every refinement in our instruments brings us closer to answering whether these spacetime tremors are real, and with them, a whole new chapter in the story of our cosmic origins. The cosmic microwave background doesn't just whisper to us through temperature, it speaks in polarized light, a subtle property that adds another layer to the universe's origin story. Imagine sunlight reflecting off the ocean, its waves aligned in specific directions after bouncing off the water's surface. The CMB's polarization works similarly, carrying imprints of its last interactions with matter in the early cosmos. This faint twisting of light waves, invisible to the naked eye, splits into two distinct patterns, E modes and B modes, each revealing a different chapter of cosmic history. E modes, the simpler of the two, emerged when the CMB's photons last scattered off electrons during the universe's toddler phase, around 380,000 years after the Big Bang. These patterns look like radial spokes or curling petals, mapping the density variations that seeded galaxies. But their real power lies in what they tell us about re-ionization, the epoch when the first stars flickered on, flooding the cosmos with ultraviolet light that stripped electrons from atoms once again. By studying how E modes are distorted by this later upheaval, scientists can pinpoint when those pioneering stars ignited, roughly 500 million years after the Big Bang. It's like finding fossilized bubbles in ancient rock. Each distortion marks where starlight began carving cavities in the cosmic fog. B modes, however, are the holy grail. These swirling, vortex-like patterns can't be created by density fluctuations alone. They require something more dramatic, the gravitational ripples of inflation itself. If E modes are the universe's baby pictures, B modes would be its ultrasound, capturing spacetime's convulsions during that first trillionth of a second. Detecting them would confirm inflation's most audacious predictions and reveal the energy scale at which it occurred. But there's a catch. B modes can also be forged by cosmic dust in our own galaxy or by gravitational lensing, the bending of light around massive structures. Separating these imposters from true primordial signals is like listening for a single violin in a symphony orchestra, requiring instruments of breathtaking sensitivity. Yet polarization's secrets don't stop there. Hidden within these patterns might be traces of the universe's first magnetic field's weak, primordial forces that could have been amplified by inflation or seeded by exotic particles. Some theories even suggest that certain B-mode patterns could hint at cosmic strings, hypothetical defects in spacetime left over from the universe's fiery birth. These aren't just abstract ideas, they're potential bridges between cosmology and particle physics, offering clues about forces that operated at energies no collider will ever reach. What makes polarization so revolutionary is its specificity. Temperature tells us what happened, polarization tells us how. It's the difference between knowing a storm passed through and being able to reconstruct its wind speed, direction, and duration. As next-generation telescopes like the Simons Observatory and Light-Bird sharpen our view of these polarized whispers, we're not just refining our cosmic timeline, we're learning to read the universe's hidden diary, written in the language of twisted light. We think we know where all the ordinary matter in the universe should be, the stuff that makes up stars, planets, and even our own bodies. But when scientists added up all the visible matter, from glowing galaxies to interstellar gas, they hit a glaring problem. Nearly half of it was missing. This is the missing baryon problem, one of cosmology's most perplexing puzzles. Baryons, particles like protons and neutrons that form atoms, should be everywhere, yet surveys kept coming up short. Where could they have gone? The cosmic microwave background, with its unparalleled view of the universe's earliest moments, has become our best tool for tracking them down. The key lies in the CMB's precise measurements of ordinary matter's density. When scientists analyze the temperature fluctuations in that ancient light, they can calculate exactly how much baryonic matter existed in the infant universe, about 4.6% of its total energy content. Fast forward to today, and observations of galaxies and gas clouds only account for roughly half that amount. So if the CMB is right, and its measurements are exquisitely precise, where's the rest? The answer might lie in the vast, invisible web stretching between galaxies. For decades, astronomers suspected these missing baryons were hiding in a diffuse, million-degree gas permeating intergalactic space, too hot to emit visible light but detectable through its subtle fingerprints. The CMB provided the roadmap. By combining its data with observations of how light from distant quasars gets absorbed as it passes through space, researchers found the smoking gun, enormous reservoirs of ionized oxygen, a telltale sign of that ultra-hot gas. These baryons aren't missing, they're just hiding in plain sight, woven into the cosmic web's filaments like invisible threads. But the story doesn't end there. The CMB also helps explain why these baryons are so hard to spot. That primordial light carries echoes of acoustic oscillations, pressure waves that rippled through the early universe's plasma. The spacing of these waves depends critically on how ordinary matter interacts with radiation. When scientists compare these CMB patterns with surveys of galaxy clustering, they find a perfect match, confirming that the missing baryons must be distributed in a specific, predictable way, stretched into thin, wispy tendrils by cosmic expansion. What's remarkable is how this solution ties together two seemingly unrelated mysteries. The CMB's snapshot of the early universe didn't just predict how much ordinary matter exists, it hinted at where we should look for the rest. Without that ancient light, we might still be scratching our heads over empty ledgers in the cosmic accounting books. Instead, we're piecing together a universe where matter isn't lost, just transformed, scattered across the voids in forms we're only now learning to see. And the hunt continues. New telescopes designed to detect X-rays from that superheated gas, along with advanced computer simulations guided by CMB data, are closing the gap further. Every time we reconcile another fraction of those missing baryons, we're not just solving a puzzle, we're confirming that the universe, even in its most elusive details, still follows the rules written in its oldest light. Long before galaxies lit up the cosmos in their modern splendor, the universe endured a profound transformation, a reawakening after hundreds of millions of years of darkness. This was the Epoch of Re-ionization, when the first stars and galaxies pierced the cosmic gloom, flooding space with enough ultraviolet light to strip electrons from hydrogen atoms for the second time in history. The cosmic microwave background carries scars from that celestial revolution, etched into its polarized light like a fossilized record of the universe's adolescence. To understand why this matters, rewind to the universe's so-called dark ages. After the CMB was emitted, space was filled with neutral hydrogen gas, a cold, featureless fog that absorbed starlight like a cosmic sponge. But around 400 million years after the Big Bang, something extraordinary happened. the first stars, monstrous giants hundreds of times more massive than our Sun, flickered to life. Their intense UV radiation began ionizing the surrounding hydrogen, carving transparent bubbles in the fog. Over millions of years, these bubbles grew and merged like melting ice sheets in reverse until the entire universe became ionized once more. The CMB's polarization patterns, particularly its E-mode signals, preserve the timing and violence of this process. Here's how it works. As CMB photons journeyed across the cosmos, some encountered free electrons from re-ionization. These collisions imprinted a subtle twist or polarization on the light. The scale of these twists tells us when re-ionization occurred not as a single instant, but as a drawn-out crescendo. Data from Planck and WMAP reveal that the universe was about halfway re-ionized by the time it was 550 million years old, with the process completing by around 900 million years. That's shockingly late in cosmic terms, meaning the first stars and galaxies took far longer to illuminate the cosmos than many theories predicted. But the CMB doesn't just give us a timeline, it hints at the nature of those first luminous objects. The patchiness of re-ionization's fingerprint suggests early galaxies were inefficient at ionizing their surroundings, leaking only a fraction of their UV light into intergalactic space. Some models even propose that exotic objects like supermassive black holes or dark matter annihilations may have contributed, leaving their own subtle marks in the polarization data. Perhaps most intriguing is how re-ionization connects to the universe's larger story. The same process that made space transparent also set the stage for galaxy formation, as ionized gas could no longer collapse into small clumps, funneling matter instead toward massive structures. The CMB's polarization is more than a relic. It's a bridge between the first starlight and the cosmos we see today, a reminder that even in the darkest epochs, the seeds of everything were already taking root. Those tiny temperature variations in the cosmic microwave background, those barely their flickers of hot and cold, are like cosmic hieroglyphs waiting to be decoded. At first glance, a difference of 1 part in 100,000 might seem insignificant, like spotting a single grain of sand on an endless beach. But these fluctuations are the universe's way of whispering its earliest secrets, revealing a cosmos that wasn't silent after the Big Bang, but alive with sound. Picture the newborn universe as a vast, seething ocean of plasma, a roiling soup of particles and radiation. When gravity tugged slightly harder in one region, pulling matter together, pressure from the trapped photons pushed back, creating waves that rippled outward. These weren't gentle ripples, they were seismic vibrations, cosmic tsunamis racing through the primordial soup at over half the speed of light. The CMB's temperature variations are snapshots of those waves frozen in time, capturing the moment they were imprinted on the universe's first light. What's astonishing is how predictable these patterns are. The physics of sound waves in a hot plasma dictates precise relationships between wavelength and amplitude relationships that show up perfectly in the CMB's fluctuations. It's as if the universe left behind a tuning fork, vibrating at frequencies that let us reconstruct its earliest moments. The most prominent of these patterns, called the acoustic peaks, correspond to waves that had just enough time to compress once, twice, or 3 times before the universe became transparent. Their spacing acts like a cosmic ruler, measuring the universe's geometry and composition with staggering precision. But the story doesn't end there. The height of those peaks reveals another layer of the cosmic recipe. The first peak's strength tells us the total density of matter in the universe, while the second and third peaks expose the balance between ordinary matter and dark matter. Ordinary matter, with its strong interactions with radiation, suppressed certain oscillations, while dark matter immune to light's push let gravity amplify others. It's like listening to an orchestra where each instrument plays a different note of the universe's composition, and the CMB is our sheet music. Then there's the unexpected harmony between these ancient sound waves and the cosmos we see today. The same density variations that created the CMB's hot and cold spots grew into the galaxies and voids we observe billions of years later. By comparing the CMB's fluctuations with modern galaxy surveys, scientists have found an eerie match, proof that the seeds of today's cosmic web were sown in those first chaotic moments. Yet some mysteries remain. Why do certain large-scale fluctuations appear weaker than expected? Could there be primordial magnetic fields or exotic particles subtly altering the CMB's symphony? Every new measurement tightens the net around these questions, turning the CMB's temperature map into both an answer key and a riddle book. Those faint variations aren't just relics, they're a living language, one we're still learning to speak. And with each translation, we're reading deeper into the universe's first diary entry, written in the language of heat and sound. The cosmic microwave background has become a cornerstone of modern cosmology, but it's also at the heart of one of the biggest mysteries in science today. When researchers use the CMB to calculate how fast the universe is expanding, they get a slightly different answer than when they measure nearby galaxies or supernova. This mismatch, known as the Hubble tension, isn't just a minor discrepancy. It's a full-blown cosmic puzzle that could either expose flaws in our measurements or, more thrillingly, point to entirely new physics lurking in the fabric of reality. So how does the CMB factor into this? When scientists analyze the cosmic microwave background's temperature fluctuations, they're essentially reverse engineering the universe's expansion history. The spacing of those acoustic peaks, the frozen sound waves from the early cosmos, acts like a cosmic speedometer, revealing how quickly space has stretched over billions of years. Based on this, the Planck satellite's CMB measurements suggest the universe is expanding at about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-years, a galaxy appears to speed away from us 67 kilometers per second faster. But here's where things get interesting. When astronomers measure the expansion rate using more local methods like tracking the brightness of pulsating stars called cepheids or observing the light from distant supernova, they consistently get a higher number, around 73 kilometers per second per megaparsec. At first glance, a difference of 6 might not seem like much, but in the precise world of cosmology, it's a glaring inconsistency. These aren't rough estimates. They're among the most tightly constrained numbers in science, each backed by decades of painstaking observations. The real question is why. One possibility is that there's an unaccounted-for error in one of these measurements, maybe hidden biases in how we calibrate distance markers or subtle inaccuracies in our models of stellar physics. But the more tantalizing option is that the discrepancy is real, signaling something fundamental we've missed about the universe. If the CMB and local measurements can't agree, it might mean our understanding of dark energy, the early universe, or even gravity itself is incomplete. Some theories propose that dark energy isn't constant but evolves over time, subtly altering the expansion rate in ways we haven't accounted for. Others suggest the existence of dark radiation, an extra, unknown particle left over from the Big Bang that could have influenced the CMB's signature. There are even wilder ideas, like a brief second phase of inflation or modifications to Einstein's theory of gravity on cosmic scales. Each of these would leave fingerprints in the CMB's detailed patterns, and scientists are scouring the data for clues. What makes this tension so compelling is that it's not going away. As measurements grow more precise, the gap persists, ruling out simple explanations. The CMB remains our most trusted map of the early universe, but if it's leading us to a different expansion rate than what we see today, we're forced to ask, is our cosmic ruler broken, or are we standing on the brink of a revolution in physics? The answer might be hidden in those ancient microwaves waiting for us to listen just a little closer. Among the most tantalizing ideas in modern cosmology is the possibility that our universe isn't alone, that it's just one bubble in an infinite cosmic froth of parallel realities. While the multiverse might sound like science fiction, some physicists argue that the cosmic microwave background could contain subtle hints of these other universes. One of the most debated anomalies is the so-called cold spot, a mysterious region in the CMB that's significantly cooler than its surroundings, stretching across nearly 1 billion light-years. At first glance, it might seem like a statistical fluke, but when combined with other oddities in the CMB's large-scale patterns, some researchers wonder if we're seeing the gravitational imprint of a neighboring universe brushing against our own. The cold spot isn't the only anomaly fueling speculation. The CMB also exhibits strange asymmetries. One hemisphere of the sky appears slightly warmer than the other, and certain large-scale fluctuations are weaker than inflation theory predicts. While these could simply be quirks of cosmic variance, they align eerily well with what some multiverse models suggest. In certain versions of the theory, our universe bubbled off from a larger multiverse during inflation, and the gravitational tug of adjacent bubbles could have left faint scars in our CMB. It's like finding fingerprints on a window, evidence that something beyond the glass once pressed close. But before we jump to conclusions, it's worth noting how hotly contested these ideas are. Critics point out that the cold spot could just be a vast cosmic void, a region where matter is unusually sparse, stretching and cooling CMB photons as they pass through. Others argue that the statistical significance of these anomalies isn't strong enough to overthrow standard cosmology. The beauty of the CMB, though, is that it gives us a way to test these wild ideas. If a neighboring universe really did interact with ours, it might have left distinct patterns in the CMB's polarization or gravitational lensing signals, patterns that next-generation telescopes could hunt for. What's fascinating is how the multiverse debate reveals the CMB's dual role. It's both an anchor for our most rigorous physics and a canvas for our boldest speculations. Even if the anomalies turn out to be mere cosmic noise, they remind us how much we still don't understand about the universe's birth, and if they're real. The CMB might be our first glimpse beyond the edge of reality as we know it, a whisper from a place where the rules of physics could be utterly alien. Until then, those faint microwaves keep us questioning, not just about how our universe began, but whether it's the only one out there. The cosmic microwave background is often described as a near-perfect snapshot of the early universe, but perfection, it turns out, has its quirks. Among the most puzzling are the so-called axis of evil and other large-scale asymmetries that defy our expectations of how the cosmos should behave. These aren't just minor wrinkles in the data, they're cosmic anomalies that challenge some of our most fundamental assumptions about the universe's birth and evolution. Take the axis of evil, for instance. This eerie pattern aligns several large-scale features of the CMB along a particular axis in space, as if the universe has a hidden preferred direction, something that directly contradicts the cosmological principle, the idea that the universe should look the same in all directions on large scales. It's like drawing a map of Earth and discovering all the continents inexplicably line up along a single longitude. Some researchers argue this could be a statistical fluke, a cosmic coincidence in a dataset as vast as the CMB. But the odds of such an alignment happening by chance are slim, leaving others to wonder if we're seeing the fingerprints of a deeper, unseen structure in spacetime itself. Then there's the CMB's hemispherical asymmetry. One half of the sky is subtly but measurably warmer than the other. Imagine baking a loaf of bread and finding one side consistently crispier, no matter how evenly you heat the oven. Standard inflation theory predicts a uniform universe, so this lopsidedness is hard to explain. Could it be evidence of an uneven inflationary expansion, where space stretched faster in one direction than another, or perhaps the remnant of a collision with another universe during the Big Bang's chaotic aftermath? Even stranger is the cold spot, a vast region of the CMB that's significantly cooler than its surroundings. At first, astronomers thought it might be a colossal void, a cosmic desert where matter is unusually sparse. But surveys found no such void large enough to explain the temperature drop. Alternative explanations range from exotic physics, like a knot in spacetime's fabric, to the far more speculative idea that it's the imprint of a parallel universe brushing against our own. What makes these anomalies so compelling is that they're not just isolated oddities. Together, they form a pattern of deviations from what our best theories predict. If they were mere statistical noise, we'd expect them to be randomly distributed. Instead, they cluster in ways that suggest, however faintly, that there might be gaps in our understanding of cosmic inflation, dark energy, or even gravity itself. Yet skepticism remains. The CMB is a noisy signal, and our observations are limited by the fact that we're stuck inside a single universe with only one sky to observe. Some of these anomalies might vanish with better data or more refined analysis, but if they persist, they could force us to rewrite the story of the universe's birth. After all, science advances not when the data fits our expectations, but when it surprises us, and the CMB's quirks are among the most tantalizing surprises cosmology has ever offered. Whether they are clues to new physics or cosmic red herrings, they remind us that the universe is always more mysterious than we dare to imagine. The cosmic microwave background has already revolutionized our understanding of the universe, but we're far from done listening to its whispers. A new generation of telescopes, more sensitive than ever before, is gearing up to scan those ancient microwaves with precision that would have been unimaginable just a decade ago. At the forefront is the Simons Observatory, perched high in Chile's Atacama Desert, where thin, dry air offers a crystal-clear view of the cosmos. This ambitious project combines multiple telescopes with cutting-edge detectors, designed to map the CMB's polarization in exquisite detail. Its goal, to hunt for the elusive B-mode signals that could confirm cosmic inflation's most dramatic predictions, while also probing the nature of dark matter and the ghostly mass of neutrinos. But the Simons Observatory is just the beginning. The even more ambitious CMB S4 project, slated for the 2030s, plans to deploy an array of telescopes across the South Pole and Chile, creating what amounts to a cosmic microscope for the early universe. With over 20 times the sensitivity of current instruments, CMB S4 won't just look for primordial gravitational waves. It could measure them with enough precision to distinguish between competing theories of inflation, potentially revealing whether this explosive expansion was driven by a single quantum field or a complex interplay of forces. What sets these next-generation experiments apart is their ability to peer beyond the limits of current technology. Today's CMB maps are like listening to a symphony through a wall. We catch the melody but miss the subtleties. Future observations will be like sitting in the front row of the concert hall, hearing every instrument with startling clarity. This leap in sensitivity could uncover phenomena we haven't even predicted, anomalies in the CMB's polarization that hint at entirely new particles or forces active in the universe's first moments. One of the most exciting targets is the neutrino, the universe's most elusive known particle. These cosmic ghosts barely interact with matter, but the CMB preserves traces of their collective mass. Current estimates suggest neutrinos make up less than 1% of the universe's energy density, yet their exact mass remains unknown. Future CMB experiments aim to weigh them indirectly by studying how their slight gravitational pull altered the growth of cosmic structures, leaving faint imprints in the CMB's polarization patterns. It's like deducing the size of a ship by the ripples it leaves in its wake. Then there's dark matter's role in shaping the early universe. While we've mapped its gravitational influence, we still don't know what it's made of. Next-gen CMB telescopes could detect subtle interactions between dark matter and ordinary matter in the primordial plasma, clues that might point toward actions, weakly interacting massive particles, or other exotic candidates. Some theories even suggest dark matter might have its own dark forces, leaving unique signatures in the CMB's large-scale patterns. Perhaps the boldest promise of these missions is their potential to explore physics beyond the standard model. If inflation was driven by energies 1 trillion times higher than what particle colliders can reach, the CMB might be our only window into that realm. Bizarre phenomena like cosmic strings, hypothetical spacetime defects from the early universe, could leave jagged scars in the CMB's polarization, while theories involving extra dimensions might produce telltale patterns in how light twists across the sky. The beauty of these projects lies in their dual nature. They're designed to test our best theories, but also to stumble upon the unexpected. Just as Pensier's and Wilson's accidental discovery of the CMB transformed cosmology, these next-generation observatories might reveal anomalies that rewrite our cosmic playbook. Whether it's evidence of a multiverse, cracks in Einstein's gravity, or particles that defy known physics, one thing is certain: the oldest light in the universe still has secrets to share. And with each technological leap, we're tuning our instruments to listen ever more closely. Neutrinos are the universe's most elusive spectators. Billions pass through your body every second, barely leaving a trace. These ghostly particles, born in the hearts of stars and the fury of the Big Bang, are so light and weakly interacting that they defy easy detection. Yet their fingerprints are all over the cosmic microwave background, subtly shaping its fluctuations in ways that reveal secrets about both particle physics and the cosmos itself. When the CMB was first emitted, neutrinos were already racing through space at nearly the speed of light, their tiny masses making them cosmic speed demons. But unlike photons, which slammed into electrons and protons, neutrinos barely noticed ordinary matter. They streamed freely, smoothing out small-scale ripples in the primordial plasma like a celestial iron. This left a distinct signature in the CMB's temperature patterns, a slight suppression of fluctuations at very small angular scales, as if someone had gently blurred the finest details of the universe's baby picture. By measuring this blurring, scientists can indirectly weigh neutrinos, something even the most powerful particle colliders struggle to do directly. The numbers are staggering. Current CMB data from Planck and other observatories suggest that the combined mass of all 3 known neutrino types is less than 1/10,000th the mass of an electron, a whisper in the cosmic ledger. Yet even this minuscule heft has cosmic consequences. Neutrinos' gravity subtly slowed the growth of galaxy clusters, leaving a detectable imprint in how matter clumps across the universe. The CMB captures this tug-of-war, offering a unique way to measure what lab experiments can only hint at. But the surprises don't stop there. the CMB also holds clues about how many neutrino-like particles existed in the early universe. Some theories, like those involving sterile neutrinos or other exotic particles, predict additional varieties beyond the three we know. These would have altered the expansion rate of the early cosmos, leaving subtle shifts in the CMB's acoustic peaks. So far, the data favors the standard 3-neutrino model, but future measurements could reveal anomalies pointing to new physics. It's like finding extra place settings at the universe's first banquet, evidence of guests we didn't know were invited. What's truly remarkable is how the CMB turns cosmology into a particle physics lab. By studying those ancient microwaves, we're probing neutrino properties with a precision that would require underground detectors the size of mountains. And as next-generation telescopes sharpen our view, we might uncover even deeper mysteries, like whether neutrinos are their own antiparticles, or if they played a role in tipping the balance between matter and antimatter in the universe's first moments. The cosmos, it seems, left its faintest particles to tell some of its biggest stories. For all its revelations, the cosmic microwave background has its blind spots, frontiers beyond which even this ancient light cannot guide us. One of the most profound limitations is that the CMB can't show us the universe's true birth. That afterglow captures the cosmos at 380,000 years old, but the Big Bang itself happened nearly 14 billion years earlier. Everything before recombination, the moment electrons and protons first linked into atoms, is veiled by an impenetrable plasma fog. It's like trying to study a person's infancy by only having access to their toddler photos. We're missing the earliest, most transformative moments. The CMB also falls silent on inflation, that hypothetical trillionth of a second growth spurt thought to have shaped the universe's structure. While the background's patterns support inflation's predictions, they don't directly reveal what triggered it or how it ended. Did inflation occur everywhere at once or in staggered phases? Was it driven by a single quantum field or a cascade of exotic particles? These questions push the CMB's data to its limits, requiring us to turn to particle accelerators or gravitational wave detectors for clues. Another blind spot lies in the realm of singularities. The CMB can't peer past the Planck epoch, the first 10 to the power of -43 seconds, where gravity and quantum mechanics collide in a chaos beyond current physics. At those energies, space and time as we know them may have ceased to exist, rendering the very concept of before meaningless. The CMB's photons, born after this era, carry no memory of that primordial turmoil. Even within its observable window, the CMB has gaps. It can't distinguish between certain competing theories of dark matter, nor can it definitively explain why the universe has more matter than antimatter. These puzzles require tools like the Large Hadron Collider or neutrino observatories to complement the cosmic picture. And while the CMB maps the universe's large-scale structure beautifully, it struggles with finer details, like the formation of individual galaxies or the quirks of black hole evolution, that later telescopes must piece together. Yet perhaps the most humbling limitation is cosmological horizon itself. The CMB marks the edge of our observable universe, but it can't tell us what lies beyond. Are there other universes with their own microwave backgrounds? Is space infinite, or does it curve back on itself in ways too subtle for our measurements? These questions linger at the boundaries of science, reminding us that even our most powerful cosmic time capsule has its limits. And that's where the adventure continues, pushing past what the CMB can see, into the mysteries still waiting in the dark. The cosmic microwave background might seem like an unlikely place to hunt for clues about alien life. After all, it's just ancient light, a fossilized echo of a time long before planets or biology existed. But hidden within its subtle patterns is a story about how the universe became hospitable to life at all. Those faint temperature fluctuations, those delicate ripples in the fabric of space, didn't just shape galaxies. They set in motion the chain of events that made Earth and potentially countless other worlds possible. Think of the CMB as the universe's first draft of a blueprint. The slightly denser regions, those warmer spots in the microwave globe, became the gravitational anchors where matter pooled, eventually collapsing into galaxies and stars. Without those initial seeds sown in the universe's first moments, gravity would have had nothing to work with. The cosmos might have remained a featureless sea of gas, eternally dark and lifeless. But thanks to those fluctuations, matter clumped just enough for stars to ignite, for heavy elements to forge in stellar furnaces, and for planets to coalesce in the Goldilocks zones around those stars. In other words, the CMB didn't just map the universe's structure, it laid the groundwork for the chemistry of life itself. But there's a deeper layer to this story. The CMB's near-perfect uniformity, its temperature varying by less than 0.001% across the sky, was just as crucial as its fluctuations. If the early universe had been too chaotic with wild swings in density, galaxies might have formed too close together, leading to catastrophic collisions or intense radiation baths that would sterilize any fledgling planets. On the other hand, if space had been perfectly smooth, with no variations at all, matter might never have collapsed into galaxies at all. The CMB's delicate balance of uniformity and fluctuation wasn't just aesthetically pleasing, it was functionally necessary for a universe where life could one day emerge. This raises a provocative question. Could the CMB's specific patterns be a kind of cosmic prerequisite for life? Some scientists speculate that if the fluctuations had been significantly stronger or weaker, if inflation had lasted a fraction longer or shorter, the universe might have turned out radically different, perhaps even hostile to the formation of stable solar systems. It's a concept known as the fine-tuning problem, and while it's still debated, the CMB offers a tantalizing clue that the universe's initial conditions were, in some sense, just right. Of course, the CMB doesn't tell us where life actually exists, only that the stage was set for its possibility, but that's what makes it so profound. When we look at those microwave maps, we're not just seeing the aftermath of the Big Bang. We're seeing the first domino in a chain that led to planets, oceans, and perhaps even other civilizations gazing up at their own cosmic backgrounds, wondering if they're alone. The CMB doesn't answer the question of whether we're the only life in the universe, but it does tell us that the universe, at least, was built with life in mind. The cosmic microwave background isn't just a playground for scientists, it's also snuck its way into pop culture, becoming a subtle star of screens big and small. Take the movie Contact, where Jodie Foster's character, Ellie Arroway, hunts for extraterrestrial signals and stumbles upon something far stranger, a message encoded in the digits of pi, hidden within the CMB itself. It's a wild idea, but one that taps into the awe this ancient light, inspires the notion that the universe might have left a deliberate calling card in its oldest glow. The film took creative liberties, of course, but it nailed the CMB's eerie power to make us wonder, could there be secrets woven into the fabric of reality, waiting to be decoded? Then there's the Big Bang Theory, where Sheldon Cooper's whiteboard often scrawls with equations about the CMB, and his obsession with cosmic inflation becomes a running joke. The show's genius was turning esoteric physics into relatable humor, like when Sheldon tries to explain the CMB to Penny using a microwave and a bowl of leftover soup. It's silly, but it works because the CMB is, in a way, the ultimate leftovers, the universe's first light, reheated and stretched over billions of years. Even video games have gotten in on the action. In Destiny 2, the CMB appears as a mysterious artifact called the Cosmic Microwave Background Radiation Device, a tool tied to the game's lore about cosmic origins. It's a small detail, but one that shows how deeply this relic of the Big Bang has seeped into our collective imagination. Artists and storytellers latch onto the CMB because it's more than data, it's a symbol. A whisper from the edge of time, a tangible connection to the moment everything began. What makes these pop culture moments special isn't their scientific accuracy, it's how they transform abstract cosmology into something visceral. When a TV character points to a static-filled screen and says, "That's the afterglow of creation," it sparks curiosity. Suddenly, viewers who have never heard of recombination or inflation are asking, "Wait, the universe has a baby picture." That's the CMB's real superpower. It turns us all into detectives, squinting at the cosmic static and wondering what stories it might tell. And maybe that's the point. Science doesn't exist in a vacuum, it thrives when it collides with art, humor, and human curiosity. The CMB's cameos in pop culture aren't just Easter eggs for physics nerds, they're invitations. A reminder that the universe's oldest light doesn't belong only in textbooks. It belongs to anyone who's ever looked up at the night sky and felt that tug of wonder, that itch to unravel the biggest mystery of all, where we came from. One of the biggest myths about the cosmic microwave background is that it marks the edge of the universe, some distant wall where space suddenly stops. But here's the truth, that ancient glow isn't coming from some faraway boundary. It's all around us in every direction, even in the empty spaces between stars. Think of it like standing in a dense fog where the mist stretches endlessly in every direction. The CMB isn't the edge of the fog, it's the fog itself, a remnant of when the entire universe was filled with glowing plasma. When we detect those microwaves, we're not looking outward toward some cosmic perimeter, we're peering backward in time, catching light that's been traveling for nearly 14 billion years, from a moment when space itself was hot, dense, and utterly unlike the vast, cool expanse we see today. Another common misconception is that the CMB somehow disproves the Big Bang. If anything, it's the opposite. This faint glow is one of the strongest pieces of evidence we have that the universe began in a hot, dense state. Skeptics sometimes point to the CMB's near-perfect uniformity and ask, how could something so smooth come from an explosion? But that's missing the point. The Big Bang wasn't an explosion in space. It was the rapid expansion of space itself, carrying matter along with it, and those tiny fluctuations in the CMB's temperature. They're the seeds of structure, the slight imbalances that gravity amplified over eons into galaxies and clusters. Far from contradicting the Big Bang, the CMB's patterns align almost perfectly with what the theory predicts. Then there's the idea that the CMB is cooling down as the universe expands, which sounds intuitive, but it's not quite right. The background isn't losing heat like a fading ember. Instead, the light's wavelength is being stretched by the expansion of space, shifting from visible light to microwaves over time. It's like drawing on a balloon and then inflating it. The marks don't disappear, but they get fainter and more spread out. This redshifting is why the CMB appears to be just a few degrees above absolute zero today, even though it started as a blazing glow. The energy didn't vanish, it thinned out, diluted by the growing vastness of the cosmos. Some even claim the CMB is just interference, a mundane artifact of Earth's atmosphere or our own technology, but that ignores the overwhelming evidence. The same signal has been detected by satellites in space, far from atmospheric distortion, and by ground-based telescopes in the driest deserts on Earth. It matches the precise thermal signature predicted by Big Bang cosmology, and its fluctuations align with independent observations of galaxy distributions and dark matter. If the CMB were mere noise, it wouldn't sync up so perfectly with every other clue we have about the universe's history. The most poetic misconception, though, is that the CMB is silent, just a static hum with no deeper story. In reality, those microwaves are anything but random. They're a cosmic symphony, carrying the echoes of primordial sound waves that once rippled through the infant universe. The patterns we see today are the frozen notes of that ancient music, a record of how matter and energy danced together in the cosmos's first moments. Far from being a mystery or a contradiction, the CMB is our most direct line to the universe's birth, a message from the dawn of time, patiently waiting for us to decode its secrets. There's something deeply humbling about realizing the light hitting your eyes right now, the glow from your screen, the sunlight filtering through the window, is part of the same cosmic story as the cosmic microwave background. That faint microwave static isn't just a scientific dataset. It's a mirror held up to existence itself, forcing us to confront questions that have haunted philosophers for millennia. What does it mean to live in a universe with a beginning? If time had a 0 point, does that imply there was ever a before? The CMB doesn't just answer these questions, it reframes them, turning abstract musings into measurable reality. Consider the nature of time. For centuries, thinkers like Immanuel Kant argued time might be an illusion, a construct of human perception. But the CMB tells a different story. Time has a direction, an arrow forged in the heat of the Big Bang. Those microwaves are a one-way message from the past, a receipt proving the universe has aged. And yet, the further back we look, the stranger time becomes. Near the Big Bang, the rules we take for granted cause and effect, the steady tick of seconds break down entirely. The CMB marks the furthest point we can peer back before physics, as we know it dissolves into mystery. It's both a boundary and an invitation, hinting that our everyday experience of time is just a narrow slice of a far weirder reality. Then there's space. The CMB's near uniformity suggests something startling. Every inch of the cosmos we see today, every galaxy, every star was once crammed into a volume smaller than a grapefruit. The space between your fingertips as you read this, that's stretched, expanded over billions of years from a primordial near-nothingness. This isn't just a mind-bending fact, it reshapes how we think about here and there. The chair you're sitting on, the ground beneath your feet, all of it was once part of that same scorching plasma we now detect as microwaves. The CMB erases the illusion of separateness, revealing a universe where everything is fundamentally connected by shared origins. But perhaps the most profound philosophical jolt comes from the CMB's role in measuring the universe's geometry. For ages, humans wondered, is space infinite or does it curve back on itself? The CMB answered with eerie precision. The universe is flat to within a razor's edge, meaning parallel lines will never meet nor diverge. This isn't just a geometric quirk, it implies a cosmos that could stretch on forever, an endless expanse of galaxies beyond our horizon. Infinity isn't just a concept anymore, it's a measurement, one that forces us to grapple with whether everything could truly mean everything, and what about us. The CMB's existence is a quiet rebuke to the idea that humanity occupies some privileged place in the cosmos. That light has been traveling for nearly 14 billion years, indifferent to our arrival. We're latecomers to a universe that got along just fine without us for eons. Yet here's the paradox. It's only because conscious beings evolved that the CMB's story can be told at all. In a universe devoid of observers, those microwaves would still exist, but their meaning would go unread. The CMB doesn't just describe the cosmos. It invites us to wonder whether the cosmos, in some deep sense, needs observers to give it meaning. This interplay raises a haunting possibility. What if the CMB's properties, its delicate balance of uniformity and fluctuation, aren't just random but necessary? Without those precise initial conditions, galaxies might never have formed, stars might never have ignited, and life might never have arisen. Some philosophers and physicists see this as evidence of a fine-tuned universe, one where the constants of nature seem eerily tailored to allow complexity. Others argue it's just survivorship bias we're here to notice because the dice happen to roll our way. But either way, the CMB forces us to confront a humbling truth. Our existence is tied to quantum ripples from the universe's first moments, a cosmic lottery we didn't know we'd won. In the end, the CMB does more than illuminate the past, it reshapes how we see ourselves. That faint glow is a reminder that we're not just in the universe, we're of it, stardust tracing its lineage back to a shared origin. Every philosophical question about purpose, scale, or meaning now plays out against the backdrop of an expanding cosmos, one whose first light still lingers in the void. The CMB doesn't give us answers, but it gives us something better, a universe vast enough, strange enough, and rich enough to keep us questioning forever. The cosmic microwave background is more than ancient light. It's a living bridge between the universe's fiery birth and the cosmos we inhabit today. Every photon carrying that faint microwave hum has traveled across 14 billion years of expanding space, threading together moments so distant they defy comprehension. This light doesn't just confirm the Big Bang, it transforms abstract theory into something tangible, a relic we can map, measure, and interrogate. From the discovery of dark energy's relentless push to the gravitational fingerprints of dark matter, the CMB has rewritten astronomy's playbook, turning speculation into hard evidence. But what makes this glow truly extraordinary is its unfinished story. With each technological leap, from the first crude radio antennas to today's exquisitely sensitive space telescopes, we've peeled back another layer of its mysteries. The CMB started as a cosmic curiosity, became a cornerstone of cosmology, and now stands as a portal to physics we can't yet imagine. Future observatories, like the upcoming LightBird mission or ground-based arrays with detectors chilled to near absolute zero, won't just refine our measurements. They'll test whether inflation left primordial gravitational waves etched in the CMB's polarization, whether dark energy evolves over time, or if hints of a multiverse linger in large-scale anomalies. The most thrilling possibility, the CMB might hold answers to questions we haven't even thought to ask. When Penzias and Wilson first puzzled over their annoying static, they had no idea they were hearing the echo of creation itself. Today's anomalies, the cold spot, the axis of evil, the hemispheric asymmetries, could be tomorrow's revolutions, clues to forces or dimensions beyond our current models. Science thrives at the edge of the unknown, and the CMB is one of our sharpest tools for pushing that edge further. Yet beyond the data and equations, the cosmic microwave background does something even more profound. It connects us to the universe's grand narrative. That light is our shared heritage, the same radiation that bathed the first atoms, that witnessed the birth of stars, and that now falls on Earth as a whisper from the void. In a cosmos too vast to comprehend, the CMB grounds us. It's proof that we belong to something unimaginably ancient and dynamic, a story still unfolding, with every observation adding a new sentence. So while we marvel at the CMB's scientific triumphs, its role in weighing neutrinos, mapping dark matter, or testing inflation, let's not forget its deeper gift. It reminds us that the universe is alive with mysteries, that curiosity is our compass, and that every answer reveals new questions. The oldest light in the cosmos isn't just a window to the past, it's a beacon for the future, guiding us toward discoveries waiting just beyond.